we went deep into graphical models, right? So we looked into structure estimation in latent tree graphical models, and we saw that it was more involved compared to just looking at graphical relationships on just observed variables, right? But we argued that in almost any practical application you will have hidden variables, because you cannot possibly measure everything that affects these observed variables, right? And a lot of when it comes to machine learning problems, the aspects of how to find this hidden space is one of the core problems. And that's where, in the earlier classes, we also looked at spectral methods as a way to get to these latent dimensions or latent space, right? The simplest one was principal component analysis, where it was linear dimensionality reduction, and then we went into these class of latent variable models, topic models, Gaussian mixtures, hidden Markov models, and showed how going from matrices to tensors can help you learn the parameters of this model with guarantees, right? So that was great, right? So it was this method of moments as being an alternative to expectation maximization, and it came with a lot of advantages and also some disadvantages. So what are some other alternatives, right? So we've talked about learning graphical models. We focused a lot on learning structure of graphical models. And when it comes to parameter estimation, we mostly limited to discrete variables in the previous classes to as an initial starting point. But in practical applications, right, it can be arbitrary continuous distributions. So how do we model the latent space? How do we then learn this efficiently, right? That's an open problem, right? So I'll briefly talk about, generative models. And if I want to have general non-parametric ways to estimate a generative model, a popular approach is, right, using what's known as variational approximation. And for that reason, these are called variational autoencoders. So we'll kind of quickly go over what are some principles behind this and how does it relate to probabilistic models we talked about in the previous classes, right? So here, instead of limiting to just discrete or Gaussian or some parametric distribution, what we want to ask is, give me a model for some arbitrary, right, distribution of data. For instance, I have images, tell me what is the probability distribution over these images, right? I mean, there you can't assume discrete, Gaussian, or some simple distribution, right? I cannot just have a parametric assumption, and that's what, was this kind of difficulty of using these classical methods, right, on modern machine learning problems. And so using neural networks is a way to get around the expressivity problem, right? So we can have good expressive models with neural networks. And in the next class, we'll go deeper into what is the expressive power and how we can analyze that in neural networks. But in this class, I just want to quickly connect thinking both of probabilistic models as well as neural networks together in the same frame. How does VAE, right, kind of bridge that gap? So we'll go over this quickly, and we'll also go over how we can model uncertainty better using probabilistic models as opposed to just neural networks. And then in the next class, we can go deeper into neural network theory. How many of you have used VAEs or looked into them? Okay, quite a few. So good. So there is good awareness of these models, right? And again, nowadays GANs tend to be better than VAEs, and we'll, the later part of the class I'll discuss about GANs. But what is the principle behind VAEs, right? So you can think of this as nonlinear dimensionality reduction. if you go back to the PCA explanation we had, the main idea was, right, there is some latent space that generates my distribution, right? In case of PCA, it was just simply Gaussian, right? Both the hidden and the observed variables were Gaussian. Because if you're doing PCA on just covariance matrix, that's what it amounts to, right? That's, if you think of that as a probabilistic model, it's simply Gaussian random variables. The hidden variable has lower dimension than the observed one. Now, if you want to think about now a nonlinear latent variable model where I have flexibility in modeling this distribution, right? I can ask, can I now learn some arbitrary distribution, right, for generating my data? And I typically also want to go the other way, right? So I don't just want to start with hidden variables and take samples of my variable x, but I also want to say, given these observations, what is the hidden variable, right? I also want to be doing inference. And you can, do the inference just with Bayes rule, right? Because I can ask, what is, sorry, this, I wrote the other way, right? I wrote the posterior. So this is x given z, and I can ask what is p of z given x. Right, but the challenge with Bayes rule is, first of all, you don't know p of x, right? And you're learning this, you have to compute posterior in high dimensions. This is challenging. And what the VAE does is to do a variational approximation, which amounts instead to say, I'll use a different distribution to model how z generates x. I'm sorry, again, I messed up, right? So how I go from x to z, right? So that is now the posterior distribution. I'm now going to use a different one. I mean, obviously, the Bayes rule here could be violated, right? You are not directly computing using the Bayes rule. But the idea is maybe this is easier to now directly train with two different distributions rather than one, right? So one is called the encoder, the other is called the decoder, right? So that's why an autoencoder means you have both encoding and decoding. So encoding means you go from your observed space to latent space. Decoding is then from latent space back to the observed space, right? And ultimately you want the two to match. And in the variational encoder, you want these distributions to match, right? In the sense, right, they should approximately satisfy the Bayes rule, but you also have the flexibility. And so that's the idea of trying to now use two distributions. So how can I think of this if I want to just do maximum likelihood, right? Because I could ask, if my goal is to find a distribution of the observed data, my goal could be just to maximize this likelihood, right? But we know this is hard, right? Because if I have now images, first of all, I can't use a simple parametric class. And if I now use a neural network instead, I know I cannot just directly fit this in the observed space. I should have some latent space of variables. And so I want to be able to go back and forth between the latent space and the observed space. And that's why we'll now try to approximate the maximum likelihood using an encoding and a decoding distribution. That's the overall idea. Any questions here? So there is a simple way to kind of come up with bounds that do not, as I said, if our goal is to compute the maximum likelihood estimator, it's hard. I can go through essentially optimizing a bound instead of this, right? It's not going to be exact maximum likelihood by but it's a bound that is easier and tractable to optimize. And that's actually a very simple bound, right? So first of all, I want to like find now also this joint distribution with the latent space. And then I can just do this, right? I can. So here, so far, it's equality, right? Because now I'm not just directly looking at maximum likelihood distribution on observed space. I also want to incorporate my variables in the latent space and look at this joint distribution. But what I care about is fitting to the observed data, right? Because I don't have the hidden variables. So this is a natural thing to do. And so now what we can do is ask, can I look at, so this is now I can think of it as expectation, but I'll now introduce a new distribution. And I can again, this is just equality, right? So I can multiply and divide by some distribution Q, right? Q of z given x. And if you recall, that's what we were using to approximate the posterior, right? We will come to that in a minute. But so far, this is equality, right? So I can just always divide and multiply with any quantity. And in this case, it's expectation. And what now we'll use is the Jensen's inequality. If you recall the expectation and log, I can switch. And then in that case, you have a lower bound. So I'll just switch the two and, right, in this case, you have the log going inside, right? So it's log of P of xc. Right, that's it. Right, simply Jensen's inequality, and this is known as elbow. It's evidence lower bound optimization. So if I'm now, instead of maximizing here the left-hand side, I'm going to maximize the right-hand side. And in general, the two are not the same, right? So I am losing out, right? Because right there you could attain now a different maximum here compared to this, but at least it's a lower bound, so that's a nice thing. And so this is called variational approximation, right? So I'm now, instead of optimizing for maximum likelihood, I'm going to optimize for the elbow, right? So it's just a simple Jensen's inequality. And another way to view this, right? So this is a lower bound. So what is the difference, right? So the difference between, so if I take log P of x minus the elbow, again, you can just write it down yourself, but I'm gonna just, to just kind of explain the intuitions, I'm just writing down. Right, so the difference between the likelihood and this lower bound is this Kullback-Leibler distance between the posteriors. So the problem is I want to avoid computing this, right? So I don't know how to compute this. So I don't want to deal with it. So conveniently now I've gotten rid of that. So I can now do this optimization easily because I'm using Q to now give me an approximate posterior, right? So the job of Q is to go from x to z, right? So it's you want to be able to find a way to sample z given x, and the job of P is the other way, right? It's like now given z, I want to sample x. So they both have their separate roles, and it's easy, right? So I can optimize over both P and Q on this elbow, and that's a variational autoencoder. Okay, so I can use two different neural networks, right? So I can have like, you could use convolution if it's images, right? So those are details. But the whole idea is I've now made my problem simpler because I have the encoding and decoding distributions to be different. And it relates to maximum likelihood through this lower bound property. Any questions here?
So are you still integrating over the elbow, or are you still integrating over the native variable?
Yes, right, because it's expectation, right? So this expectation would be here. This Q will be the expectation over Q means you're taking expectation with respect to this distribution, right? And that involves Z. And you should, right? Because the idea is, you want to look at, you only have your observed data, right? So you have to integrate over Z. That's the only way you can fit to your observed data. But the idea is now it's easy to integrate over Z, right? So typically, right, you would start with something simple like a Gaussian distribution, right? And then you have a neural network, you can compute this. Or you can also approximate it using stochastic variational inference or stochastic variational approximation. The idea is instead of this expectation being exact, you just look at gradients, right? Like you look at how you want to update the neural network weights at each step. So you can exchange the expectation and the gradients. That's an additional detail if you're doing this as a stochastic optimization to train the networks. But yeah, you have to, the idea is you still, you integrate over Z both here and here, right? But now I've made it more flexible because I'm now using two different distributions rather than just one. All good? Yeah, so I guess most of you have used VAEs or come across this, so I just wanted to spend a few minutes, like kind of connecting it to previous material, right? I think the easiest connection is to view it as nonlinear, right, dimensionality reduction, because in PCA you are only going between, right, like Gaussian variables to Gaussian variables. This is now arbitrary distributions. And the other aspect that connects to probabilistic graphical models we talked about was the inference problem, right? Because if you recall in the previous class when we were doing latent tree models, we said we need to infer these hidden variables. Only then we can estimate edges between hidden variables, right? If it's discrete, this is easy, right? I can just write down the base rule. But if it's arbitrary continuous distribution, I can't evaluate it and I can't optimize over it. This is hard. And that's why we'll now introduce the flexibility to have a different distribution to approximate the posterior and hope that this bound is tight, right? So, I mean, just by optimizing this bound, you're not really, it's hard to ensure it's tight, right? Because there is, the difference is this. So many times it may be off, and that may be one of the downsides of this. So there are several reasons why GANs are better than VAEs, and I'll come to it when I talk about GANs. But this is also one of them, because you could even model good distributions, right? So maybe you'll use domain knowledge and come up with good ways to say what should be the latent variables, what should be this neural network structure. But the problem is if you're not directly optimizing for likelihood, you're off, right? But you may be also off because you don't know how to model well, right? Your model itself could be wrong. But that can be overcome if your neural network has enough capacity, right? Then you don't have model approximation errors. But you do get these errors because you're optimizing the elbow and not the likelihood. Okay, so those are some considerations. With respect to why GANs are better, right? At least one immediate thing to take away is you don't have to just go by the likelihood metric, but a more flexible way to determine what's a good measure to optimize for. Right? I mean, the reason we have likelihood as a measure to optimize is because when you did maximum likelihood estimation, it has a lot of nice properties. Right, so, but then in practice, maybe that doesn't matter. Maybe for images, anyway, we don't know how to model well, and likelihood is not a great measure, right? There could be other measures that are better. And so the GAN gives that flexibility to even figure out what is that measure, rather than just go with likelihood. And so that could be a reason. On the other hand, these give you uncertainty estimates, right? So you can determine what is the likelihood of each sample, or at least approximate it. So, and there are also more sophisticated models for getting good uncertainty estimates. I won't go into them in detail, but there are these what's known as invertible models. They're pretty recent, and the whole idea is, in addition, enforce invertibility, right? So that way I don't have to use this other distribution. But then they tend to be hard to scale because invertibility could be a strong requirement. So that's another alternative. So these generative models are fast evolving, right? So, but VAE, I think, is built on a simple principle, and I wanted to just kind of give an overview of that. Great, so another aspect of why use probabilistic models, right? So this was one connection to probabilistic models. I can use them as generative models for my data, and many times if I want to be able to get to good sampling of my distribution or compute uncertainty estimates, right, I can use principles from probabilistic modeling. Another reason is, even if your task is classification, you may want uncertainty measures, right? So, the idea is not just to give an answer, but also maybe give a confidence level, right? And you may have seen in the news that, you cannot trust the current generation of neural networks, right? So there's a lot of bias in them. There's a lot of black box nature in terms of we don't know why they fail, and one aspect of that is you can't trust their confidence measures, right? So for instance, if a neural network tells you that it's 90% confident, right, about its answer, that's not a true measure, right? It's not a good, it's not the true underlying measure of the mistakes it's making. And the reason they tend to be having this calibration issue, right, that is, they don't give you a good measure of uncertainty, is because, this principle of uncertainty quantification. So the idea is there are different sources of uncertainty, right, when it comes to data. So if you think about any domain, there's one kind where there's just inherent ambiguity. So if you ask, for instance, even say ImageNet or any of the standard benchmarks, some of the images maybe just people are uncertain. They don't know what's really in that image, right? Either there is occlusion, low lighting condition, some weird texture, right? So all kinds of reasons why, right, people may themselves find it ambiguous. So that kind of uncertainty is known as aleatoric uncertainty. Even if you keep asking for more examples, you won't overcome this ambiguity, right? Because it's just inherent. The more samples you ask, the more variation you get, right? So you cannot overcome that by just asking for more data. Right, so that's why more data is not always the answer, right? If all the data is going to be of poor quality, that doesn't really help you. So that's known as aleatoric uncertainty. And the other one is called epistemic uncertainty, the other kind. And in epistemic, the idea is as I get now more data, I can reduce this uncertainty, right? So I guess the example is, you get pictures of dog. If you just have like 10 examples, that's not enough. But if I have 1,000, right, I can be more certain what a dog looks like. Because you want to cover different lighting conditions, poses, right, different contextual information. So that's known as epistemic, right? So more data there is great because now I'm getting to know that these are all the possibilities of what a dog is, and I can now reduce the uncertainty by collecting more data. And just to kind of give you some idea of what that looks like, let's say this is my function that I'm approximating using the neural network, right? Let's say it's, for instance, could be the classifier, could be regression, could be any problem, right? So, and there's some there's some uncertainty bounds around, right? Because you're not certain. And so this means that, there's just uncertainty throughout. It may not even be uniform, right? I wrote it as uniform just for simplicity. But the idea is there's like aleatoric uncertainty, right? Because I've not even told you where the data is. This is just the underlying uncertainty of the function itself you want to approximate using the neural network. But now if I add data, suppose I have only told you that data is here. I only ended up collecting data here and not in other places, right? Then there is epistemic uncertainty because the epistemic one, right, would be now even higher. There's a lot more uncertainty here because I've not seen that data. But now if I added and collected more data here, I could just bring it down to whatever was the aleatoric uncertainty. Right, so that's one way to visualize, right, what these two different sources of uncertainty look like. Any questions here?
But it seems like if you have more data, you can better estimate at least the mean or variance of this function. But it's still aleatory.
Yeah. Right, so when you're estimating the variance, right, that means, right, there is still this aleatoric uncertainty. But if you've never seen data in that region, right, or you've seen very little data, you should have higher uncertainty than in regions where you saw more data.
I see, so the variance is a sense of uncertainty.
Yeah, I mean, if you just look at variance, it combines both of them, right? And that too, assuming you've correctly estimated the variance, right? So in a neural network, first of all, you're not correctly estimating, right, what is this confidence level or uncertainty level. And I'll come to why that's the case with neural network, right? But this is just independent, right? So right now we are not talking about an estimation method. We are just talking about how the uncertainty changes depending on how many data points are collected. Right, so even if I collected infinite data points here, I would still have some uncertainty left, and that's called aleatoric. And here in this region, I have collected no data, so I could have a very high uncertainty, right? Or maybe there's 1 or 2 points, I've collected little data there. So when you're just talking about variance or uncertainty, right, there's no distinction between the two. But if you talk to Andrew Stewart here, or people who are really interested in uncertainty quantification, right? They go into the details of what kind of uncertainty it is, right? So it's not just about, okay, what is the variance? What is the source of this variance? Where is it coming from? And it's important to distinguish the two, because just collecting more data will never let you overcome this. Which also means it's not a great idea to have your answers be deterministic, right? If your function has high aleatoric uncertainty, you do want these uncertainty bounds. I mean, even if you give some answer, you want to like say, this is what I think is the uncertainty bound, right? So without giving uncertainty bounds, you can't really trust the result, right? Because it doesn't tell you much. Yeah, and the other aspect now is, so why do neural networks, where do they do, where are they weak, right? So they're weak when it comes to this epistemic uncertainty. And the reason is because what neural networks do is they interpolate, right? So they're taking data, they're fitting that data to this neural network, right? So they'll only be able to give a good function fit whenever there is data here. On the other hand, they don't know how to extrapolate beyond, right? And they haven't seen data there. So instead of giving the right uncertainty bound, they tend to be extremely overconfident in regions they have not seen data because they think it's similar to where regions where they've seen the data. So maybe this is what they think the uncertainty is in this region. And this can be very dangerous, right? So it's also known as unknown unknowns. They don't know that they don't know, right? Because they've not seen these data in this region, in this example here, right? They've not seen those variations, but they've only interpolated on this limited set of data, and because they haven't seen this data, they just expect this is also okay, right? They don't have a good way to be giving the right uncertainty bounds in these regions. So that's where they're terribly weak, and that's the reason is because they're interpolators. Right, they only worry about fitting the function within the data region where which has been given to them. Right, because when we are training them, right, or even validating them, we are telling them nothing about the data that is unseen, right, outside this domain on which or region on which they're trained. But if we ask to operate here, of course, if you're operating only here, that's great, right? But if you're operating here, you're in deep trouble. And all the researchers who are worried about the risks of AI, including me, are worried about this, right? Because in the wild, I'm like, there is no guarantee that it'll be the same scenario. Whether when it comes to autonomous driving, obviously it can be extremely different scenarios from the training data, right? Because you don't know what can come up. It may be rare, but it can happen. And in that case, we know it's going to fail pretty badly, right? Because because right now it's not fully autonomous driving, right? The idea is to always have the human be aware, but humans tend to lose attention over time. And so in that case, right, if you're not communicating with the human and giving good uncertainty measures, the human may become confident and just kind of not pay attention. Or say in face recognition, if this is used in high stakes scenario like law enforcement, and you say that, oh, I'm 90% confident this is a match, right? So the law enforcement may take measures that could put human lives at stake, right? Because they're believing this is the true confidence measure. And this is especially bad on minorities or people who have not been in the training data, right? So because they are the ones suffering because there wasn't enough data trained based on their features. And that's why I think this is a big risk for taking current AI systems trained on just standard deep learning out into the wild, because they're bound to fail whenever the training data is not covering that part of the domain.
Just a quick question. Just for us human, if even if we don't observe something we haven't seen before, the only thing we can do is find something similar to that thing, right? and we interpolate, we are doing the same, right? What?
Or you can say, I don't know, teach me.
Oh, I see. So you mean that the system should be aware that it does?
Yeah.
It doesn't. That's it.
And that's uncertainty quantification, right? It's giving you honest answers of how confident it is. Whereas in the current neural network setting, you cannot expect that because it's never thought about what will happen outside that domain of training data, right? So it won't have good uncertainty measures or confidence measures beyond the training data.
Is it possible to, let's say, add a Bayesian layer to your network so that you are quantifying uncertainty in some way? Or
Yeah. So that's kind of like that was my connection, right? So the idea is, if you train just a deterministic neural network, right, it's bad because it's only interpolating. It has no measures of uncertainty. So way around this is these Bayesian neural networks, which again combines like probabilistic, modeling and maybe variational approximations with neural networks. And so that was my kind of argument of why you would want to consider beyond standard neural networks.
Is it hard to each scenario find the worst possible case that can be happen, worst case outcome, and for example report that as your confidence interval? This is the worst possible thing that can happen, for example.
So that's what robust estimation does that, right? So, and again, there are kind of, if you go deeper into it, how do you do this in high dimensions? How do you, right, do that worst case optimization, right? And that could be framed in terms of competitive optimization in a way like GANs also, you can think of it as like in the worst case, right? Because the discriminator is kind of looking at different kind of possible ways to measure and evaluate the generator, right? So the robustness could be in terms of the worst case, and that can, adversarial training is one form of it, right? But it has, I wouldn't say it completely solves the problem, but that's one way to build robustness. But again, right, so the idea is but those would make things more robust, right? But the idea is not just to add robustness, but to make sure you have some base level uncertainty, right? So there's always some level of uncertainty. And now as you get in more data, you can reduce that uncertainty. And that's what the Bayesian method would do, right? If you have a prior where there is good level of uncertainty almost everywhere, right? So if it's never seen data, then at least you have so that's again, right? It's a choice of prior, but you can choose a prior where there's some uncertainty throughout, right? So that means if you've never seen data there, it kind of has that uncertainty level. And now as in the regions where there's more data, that uncertainty level gets to be lower.
But generally, why shouldn't we care about just in convex hull of our data set, for example? Why should we even go outside of that? I mean, if this is the goal, right? No,
the goal is to ultimately use AI in the real world, right? That means it's never a closed set, right? It's an open set. It's in the wild. You don't know what you're going to encounter. In the project we had with drones, right? The drone could suddenly encounter wind conditions. It could encounter other barriers, right? It could be asked to fly at a higher velocity than what we trained on, right? So similarly with autonomous driving, right? So we can't possibly handle all possible scenarios in training because that's too large. That's impossible even with all the world's compute to be able to handle that. And even with all that, there could be completely a new form of scenario that comes along, right? So the coverage is almost impossible to get. And the question is, what would happen there? Can the neural network at least tell you that it's highly uncertain?
Why not just tell me, I'm just looking at human then observe something new, go and, okay, that is whatever I know, right? I can perform well in this set. And if something new happened, okay, probably the first time I'm bad, then I learn that part of focus a bit more. Mm-hmm. And that's it. What can we do outside this? I mean,
Yeah, but at the very first step, you know that you don't know, right?
I know I don't know because, no, actually I thought probably this is new scenario. I have to select something to do, and then the result is I'm bad at it. I'm just, I don't know, I hurt myself.
So again, it depends on, right, the safety concerns, right? If it's like kind of a life and death scenario, probably you won't just try, right? You'd be really careful and you'd ask for help. So it really depends, right? And of course, the other thing humans have that AI doesn't at the moment are priors, right? We have such strong priors given to us by evolution. So, you're already starting at a good point when it comes to especially interacting with the physical world around us. So, but we don't have that in our AI systems to begin with, right? So in a way, those priors, if you had good priors, you would have had some notion of uncertainty throughout, right? And hopefully even low measures of uncertainty because the priors are informative. But we don't know that.
My question was that because there is no, this is really hard for me to imagine there is a way of going, beyond this is limited data. Okay, this is the best we can. I don't know how we can design something that is really good out of our training set. It's really something.
That's why you have to go beyond just the passive learning, right? It shouldn't be learning just on a fixed data set. If your goal is not just to if your goal is not just to be good in terms of just data of similar kind as training, you have to do this interactively, right? And so one setting where having good uncertainty measure will be useful is active learning, right? So again, I won't go into all the details here, but the idea is, right, like to your point, I shouldn't be just limiting to whatever data I have, right? I should go and collect the better data. So if I had good uncertainty measure, right, I realize, oh, this is such high uncertainty here, I'll go and collect new data here. But if I had poor uncertainty measure, I won't even collect the data, right? So it's like the problem's never fixed because it doesn't know that it doesn't know. Right? So that's why it's important to have this uncertainty measure, right? Because if I do, then I can do active learning, I can improve my model, right? Or I can ask the human to intervene, right? I can kind of make sure the human doesn't trust the AI too much and has other ways to overcome this, right? So there could be so much you can design once you at least know the uncertainty. And so the way around this, right, and the connection of why I brought this up is, yes, even if you're just doing kind of classification tasks, neural networks with just deterministic units are not great at handling uncertainty of the epistemic kind. And so Bayesian neural networks are kind of combination of probabilistic models with neural networks. Right, and the main idea is you have like now neural network layers where, the question of, if it's a very big neural network, how to put in priors there is also an open one, right? But a standard one is I can like look at my weights, and instead of thinking them as fixed quantities, I can put a Bayesian prior on the weights, right? Some, I don't know, zero means something for each weight, right? So just independent Gaussians as my prior, right? That's a simple starting point. So the idea is there's always some level of uncertainty, right? Throughout, and the hope is, if I'm looking off like my posterior of weights given data, as I have more data, I can sharpen my posterior.
Why not perturb the nodes itself? Because probably this is what I learned, but
yeah, so the other option is not to put uncertainty on the weights. You can also, like put uncertainty into your activations, right? A very simple one is dropout, but dropout is not dependent on data, right? So that usually doesn't give you a good measure of uncertainty. People also do other kind of stochastic sampling techniques. Based on my data, I just sample the high activations, right? So like Guneet has looked at that. So again, it's an open question of what is the most efficient way to get good levels of uncertainty to begin with as a prior. But ideally, if it's even informative and has a good inductive bias, it could help you sharpen up even better to a posterior, right? So that is the challenge. If you have like a prior which is very non-informative, that means it's good. In one way, it's good because you have uncertainty everywhere, right? So you don't have this overconfidence issue. On the other hand, very high uncertainty everywhere means it takes more data to sharpen the posterior, right? So the ideal scenario is where you have the right design of prior that kind of, if you knew what was that aleatoric uncertainty, right, you would kind of directly kind of try to incorporate that. And so if you know more about the domain, you can design better priors. And there's a lot of work to ask how to design priors. But in domains like images, it's hard to come up with that.
How do we know from neuroscience, for example, how do human, for example, simple, how does it work, whatever we have?
I mean, again, right, like it's so extremely complicated. We are very far away from measuring the priors. I mean, we have, of course, we know there are priors, right? But again, how do we even get started to measure the priors? Because we are measuring priors on all of the world around us, right? So even if it's just vision, it's like, okay, now how do I get this distribution over all possible images, right, in the brain encodes? And we don't know that. And first of all, we can't do it on adult humans, right? You have to do it at infants, like just as they are born, because after that there is learning and updating. So yeah, so I don't even know how to get started there.
I'm just curious, why can't I just have another network to estimate how safe it is or estimate the uncertainty?
So people have done that too. So because you can ask now another network to try to, like estimate what is the level of uncertainty. And again, right, the pros and cons to all this, right? So because somehow then how do you coordinate the two networks? And what if they are inconsistent in the sense? How do you make sure they are aligned well? In a sense, that doesn't solve the underlying problem, right? Because you kind of want your system to be somehow self-aware. It is uncertain rather than having an outside one.
I also feel this problem is not really good posed. I mean, we humans also have uncertainty, and we are not sure about uncertainty about uncertainty, right? You cannot really
Yes.
know that.
And the reason is it's hard to come up with, or at least standard machine learning setups don't have measures of uncertainty on even training data, right? So for instance, the images, it's like the question of is there a dog, is there a cat, right? But not like, first of all, asking humans how confident are you, if you ask them directly, you won't get a good answer, right? But are there good ways to measure how ambiguous do people think things are? Maybe a good starting point, because at least then you have some ground truth of what is the true ambiguity or the aleatoric uncertainty, right? So, and I think one of the examples was done by Ben Recht's group in UC Berkeley on, they went back to ImageNet data set, right, and then asked, redid the experiments again. So the way the ImageNet was collected was, asking, if the category is, say, bird, there were lots of images on the screen, and the annotator had to go pick which one was bird, right, or multiple ones. And also negative examples, like which one is not a bird. So, but because annotators do this very quickly, the idea is the images that are so obviously a bird have low uncertainty levels, whereas those that get picked less often have high uncertainty, right? So you can design more careful experiments to even get from humans more information about uncertainty. And that could be a way, right? If there are ways to assess what is the variation within the distribution of my training data, and can I get even some ground truth on what is some underlying ambiguity. That's, and in fact, the original ImageNet data set was collected this way, right? But that information was thrown out. I mean, same with a lot of natural language processing data sets, people use language in so many ways. It's dependent on so many factors, which part of the world, right? What is the context? What is the background of the person? So if you captured all those variations, you'd be better off, right? Because there's no one answer, there's multiple answers, right? In terms of even something as simple as sentiment, right? Maybe people think differently after they read this sentence. So one way is to capture the diversity from many annotators and use that information when training models. So that could be a way to have at least some validation of, is this doing right? Is this capturing that uncertainty? But I agree, it's not a simple kind of a math, right, formulation to pose this, because it depends also on the scenario. Okay, so to train Bayesian neural networks, again, you can use these variational approximation tricks, right? Because to compute this posterior is again hard, and I'm going to use another distribution to approximate the posterior. And if I'm doing stochastic gradient descent or similar stochastic optimization algorithm, I can update my approximation of the posterior online, right? And I can do that efficiently. So that's what some of the recent papers have done to train Bayesian neural networks. But there's still a lot of challenges, right? They still don't scale up to some of the biggest networks we have today. And with variational approximation, we are making all these approximations, right? So we don't know what is the impact it's having. And also the reason is if you don't have now, as I said, some ground truth on what is the ambiguity or some ways to test this, right? So another way would be to test it on some challenging scenarios, such as in autonomous driving, show it some scenes that weren't shown during training that's quite different, right? But then how do you come up with that? Somehow this has to, again, do with designing the experiments better and also testing these systems better. Right, so, and I think that's the reason Bayesian neural networks haven't really taken off that much, because we don't know still what to do with them. Because if it's a standard benchmark train and test, you're not going to see much advantage. In fact, you may see some degradation of accuracy, right? Because you're making all these variational approximations, and these are expensive to train. So it's an open question on how you can show whether this is the right framework or other frameworks drawing upon from uncertainty quantification to show benefits of that in some of the deep learning applications. I think the aspect that hasn't been looked at carefully is how to design the right benchmarks and experiments to show this benefit, because you won't see that in a standard leaderboard setup. Good. Any other questions, thoughts?
Generally, have we used them, for example, neural net, I'm not sure, I don't know, on anything other than image or language, or for example, on financial data, something that has totally different probably underlying system, something, I don't know, some other kind of data. Have you used them to see, for example?
People are using deep learning in so many applications, right, in across domains. And again, right, there is always the question is how much data is available, what is the task at hand, right, how much do I care about uncertainty and wrong answers, all these matter.
But I mean, isn't it possible that some of the things that we are working with, it might be for uncertainty, that there are some basic feature, dimension reduction, that just some basic feature underlying that even outside our data, possibly these are the main force behind, for example, getting something and, for example, this thing, think that it works?
So I guess what you mean is the hope is neural networks can extract features that is widely applicable everywhere, right? But that's not true if your domain is extremely rich and you've never seen parts of the domain. For instance, if you've never trained, your say for autonomous driving under night conditions, there's no way it would work, right? Or you had only very few examples of night scene. So the idea is in terms of like what is the coverage, right? And if we are thinking of real world, it's too big a space to cover everything.
But generally, has anybody used a neural net for some application and used the same trained one for something else that is kind
Yep, I mean, people are doing this as we speak, right? Companies are launching all kinds of, badly designed, ill-tested apps into the real world. And that's why I'm emphasizing this, because this is a big danger. And, many times it may be okay if it's a simple recommendation, okay, I ignore that movie recommendation, or I ignore that ad, I just get, of course, annoyed, if it's something that really targets me because I'm a woman in 30s, right? If I'm targeted with anti-aging creams, I get extremely annoyed. I even go change my gender on YouTube because I'm, so that's one level of kind of, right, things being targeted and not kind of being too personalized to what I really want, right? So it's not generalizing well to me, right? But the other, of course, extreme are cases like autonomous driving or scenarios that involve like, whether somebody's loan gets accepted, right? A crime recidivism, like determining somebody should be in jail or should be released on parole. I mean, these are all very high stakes scenarios. And, there are a lot of systems that are launched today that are already available where we don't, people think they are great, right, that they work very well. But they don't understand that these neural networks can not only give wrong answers, they can give highly confident wrong answers. A simple example of this was an app, I think Eric Topol first tweeted it and then I retweeted it, was on skin cancer that was even, I think, approved by FDA, right? So it's like, takes an image of the mole, right, says whether it's likely to be cancerous or not, right? Seems simple enough, but it turns out that all their training data had a purple marker for the cancerous ones. So for us it's like, oh, how is this happening? But this is a launched app. I mean, people were already using this. So it's right. So that's why I think this is so easy to kind of not pay attention to. If you're a company out to make profits in a very short amount of time, you launch everything, think it's working great because on your training data you got 99% accuracy, on your validation you got 99%, right? Doesn't mean anything if it's being launched in the real world. I mean, it means something, right? At least it's doing within that limited data, but it may not have great coverage at all. And there's also the aspect of historical bias, right, when it comes to, say, law enforcement and minorities, right? So they tend to be more targeted, and now on the other hand, we are also having AI systems where minorities are not getting good coverage, are not represented well. So the two together can further amplify these biases. And and I think at the root of it is uncertainty quantification. At the very least, they should be able to, say that I don't know, right? I mean, the next step is, of course, making sure everybody gets good accuracy in these systems. But at the very least, you should kind of at least be able to answer how uncertain you are on certain sample.
So is it possible to build a metric, something that under your new data, telling you that if it is far from whatever I saw before or not, and just report that as your just uncertain? That I don't know, for some reason it is very
I mean,
from my observed.
In a way, what you're asking for is I want a good generative model, right? Because if I could kind of model the input itself, I can tell you, oh, this is different, this is similar, right? But that's also a hard problem, right? In standard classification tasks, we don't worry about, right, learning the generative distribution. We just say, just give me an answer. I don't care what the input distribution looks like. And to me, I think that is an incomplete answer, right? You have to get to generative modeling. And that's why I think, the question of how to do that well is important, right? Because if you had, say, a better generative model, you don't have to just do a simple Gaussian prior here, right? You can actually go and look at, okay, is this sample highly likely or less likely, right? And how does it relate to where my training data was? Because you don't know the metric to measure, right, how similar or how different samples are, right? In something complex like image, you can't just use L2 metric because you just, right, add some small noise. For us, it's imperceptible, but in terms of the distance, that's a large distance. And that's why this is hard, right? Because unlike the simple example, I can't really tell, oh, here the sample is away from here. And that's why, the recent works try to ask, how can I use generative models even when I'm doing classification? Can I use this in a better way? But it's still an open problem to do this. I feel like they really haven't come together completely well and definitely not scaled up to real applications. Great.
What are obstacles when scaling up Bayes neural network?
So the main one is, you still first of all, these weights, right? If now you have a billion or more parameters, this is now more expensive in each step. You have to kind of update the mean and variance. And you're first of all making variational approximation because you cannot compute this posterior. So you're making all these approximations at a large scale, right? We don't know what it's going to lead to, and it's going to be more expensive to train. So, right, people so far haven't shown what is the benefit, because I guess training accuracy, they're getting better to almost, right, the same as the baseline. But I think truly assessing its benefits has to be more in this kind of scenario, right? You can't just look at validation accuracy and say, I'm beating the existing network, because that's not going to happen. Yeah, so I guess the open question here is really, how do you evaluate them, right? And you go beyond the train and test philosophy of evaluating current networks or current models. Right, that's in terms of, right, kind of in terms of asking what is this useful for. The other challenge, of course, right, if I go about asking, should I put priors on my weights or activations? What are good priors to put? Can I actually be informed by the domain well, right? That's also open. Any other questions? So that was with respect to uncertainty quantification. I want to now use the remaining time to talk about GANs and alternatives to this probabilistic modeling approach, or scenarios where earlier we were talking about robustness, right? So you want to evaluate some worst case and do the best on that worst case, right? So min-max kind of settings. So to do that, we'd have to require competitive optimization, right? So it's no longer optimizing for one objective, right? You have multiple agents, right, that compete with each other. And so I guess GAN, or generative adversarial networks, I guess probably all of you have seen it. It's impossible to miss. And the main idea is there is a generator and there is a discriminator, right? So the generator kind of generates, right, fake images, right? So it takes in some latent code, usually just Gaussian distribution, converts it into fake images, and then the discriminator has to separate the fake and the real images, right? So it's like, it should say whether an image is real or fake. And of course, to train the discriminator, you also feed in real images. So the idea is, right, I don't have a good metric to say whether this image is realistic or not, right? Because as I told you, I don't know how to measure similarity between images well. But instead, I'm going to train a discriminator that can distinguish the real and fake, right? So I'm training both the generator and the discriminator, right? So the idea is, let's say d of x is 1 by the discriminator, so discriminator says it's 1 under real images, right? I could like kind of ask for it to maximize, right, its answer. So I want my discriminator to be as accurate as possible. Right? And I also want my generator to try to fool the discriminator. And that's why this is a competition. Right, so generator tries its best to make the fake image look like real image, and discriminator does its best to discriminate the two. Right, so this is a minimax objective, and we want to ask how do we optimize this well. So
that you gave the discriminator false and real, is it you give it both of them, or you select sometimes you give this one or this one?
So the idea is to, you're giving, so again, it depends on the design, right? So the idea is you can train just on real image, right? And then it knows what a real image is. You train on fake images, it knows that it's fake. So essentially it's label data, right? It's a binary classifier. Its job is to output a binary classifier that can tell whether it's real or fake.
Isn't it just possible to just give some data to, not even data to the generator, just give the last real or fake thing as a just benefit of that generator? I mean, it's a zero-sum game, right? So one of them gets 1 if it wins this one, for example, and the other one gets 0, or vice versa. Okay, and the goal of
no, the idea is to, let me write down the objective function, because it is getting the feedback, right? That's what it is. That's how you train the generator and discriminator jointly. So the idea is you want to maximize, right, the accuracy of your discriminator. The discriminator wants to maximize its accuracy. So the idea is, let's say, it wants to say it is real image when data is really drawn from real images, right? So it's an expectation that should be, and then usually it's log, because I want to like kind of think in terms of the. So and then I have the log again. So I want to say it is fake when it is drawn from this latent distribution. And of course, the generator wants to minimize that accuracy, right? Because it wants to be able to fool the discriminator. And so this is why it's a min-max problem or a zero-sum game. Right? Yeah, and the whole idea is, in the sense, right, like you can also think in terms of robustness, because instead of like the generator minimizing a fixed loss, it's looking in some sense the worst case, right, over a family of loss functions. Right, that's the other interpretation as a robust estimation problem. The worst case is if I have a really powerful discriminator, right, that can really tell apart which is real and fake. Even in that worst case scenario, I can fool the discriminator. And that's the angle from the robustness viewpoint. Right? I'm not going to just optimize over a single objective, right, fixed objective. Instead, I'll look at a family of objectives and look at the worst case, and I want to optimize for that. So you can think of this as a min-max estimator. Right? We briefly mentioned that in the beginning of the class. And that's why they tend to be better in practice because, right, even if I'm doing like VAE, I'm like, right, making choices of family of distribution here, right, and then I'm using these variational approximations and so on. Whereas here it's more flexible. I'm looking at, right, different possible discriminators. I want to ask, even if I have a powerful discriminator, can I fool that? Any questions here? So the question of how to optimize this, right, that's what I want to focus on here because there are many aspects, right, of like GANs, and there's a lot of still, I think, mystery. I wouldn't say it's all a solved problem, but I want to focus on the optimization angle. Because unlike the optimization problems we saw before, these are two agents, right? It's a competitive optimization problem. And we need to have different considerations and different analysis to see what's going on here. So I will just, this was the motivation. Let me just look at min-max over some objective. Right? Let's say X and Y are my two players. I just do this because I just want to, focus on the optimization side of it. Right? So what's different when it comes to, let's say, just single agent, right? So let's write down what's similar, what's different. Because we've talked extensively of just single agent optimization.
Do we know, for example, this you design, is it, for example, even fixing X, for example, when you want to, assume that I give you this X to start with,
Okay.
Do I know that, for example, this maximization for me as a y, is it, for example, concave function? Is it a concave function, U convex function of X, something like that?
So those are the cases where we can analyze, right? So right. Similarly, I guess, and that's the question, that's the thing, right? What are kind of tractable problems here? But before we go there, what do you see some differences between the two? Just something that just immediately comes to your mind.
So for certain cases of X, where in the distribution where it's like unlikely, you can care less about, like, let's say, minimizing the loss there. But if it's a joint distribution, Y can be picked so that they focus, they like increase the relative probability of you being that part of the distribution. So you have to care about that, about like minimizing the loss there as well.
So I guess what you mean is you have to care now there are two agents with their own objectives, right? So whereas earlier your goal was just to kind of go to the minimum here, right? So let's say if the function was like this, you knew you wanted to get here, right? But here you have two agents, right? So they have competing objectives. And so so you can't just measure based on one objective of whether, right, this global minimum was reached, which is what we did in the single player. So what do we call these kind of points? Points which are equilibrium here. So the equilibrium points here, right, was local min, right? And we even came up with properties. If you recall, we had second order conditions, right, of which are stable local minimum. So what are equilibrium points here? So equilibrium point is where you don't move, right? You start there, you stay there. What's the notion of equilibrium for competitive problems?
In theory, we call them Nash equilibrium, saddle point.
Right, exactly, right? So this is a saddle point. And if you're doing constrained optimization, you would have also seen these saddle points, right? Because you introduce the Lagrangian and you want to maximize over the dual variables. So the equilibrium points are saddle points, right? So, and if you recall our discussion earlier on saddle points, it was like this horse saddle, right? There are some directions where it's descending, in others it's ascending. And we said for single agent optimization that was bad, right? I didn't want to be at a saddle point because I could improve further. But for now, these competitive optimization, I want a saddle point, because I want it to be minimum, locally at least a minimum, right, in the directions along x, and in the directions along y, I want it to be ascending. So that way it's stable, you cannot optimize further in terms of the min-max objective. Right, so those are the equilibrium points here. And of course, with game theory, it's the Nash equilibrium. And again, you can kind of, right, if it's the function is differentiable, right, you can similarly talk about like local minimum, you can ask, right, like it's a saddle point, so locally you can test for saddle points. So how will I test for saddle points based on first order and second order condition? We did this before, I just want to make sure you recall that. So what should be the first order condition for a saddle point?
The partial derivatives with respect to x and y are both zero.
Right. And then the second order, how should I now, what should be the condition?
Maximizer should be concave, so it should be negative.
So it should be only in terms of this, right, the self-derivatives.
Right.
So that should be, if it's strict, then this is also strict. Right, so these are conditions we can check for. So now the question is, how do I kind of optimize this efficiently? So it turns out that it's not as simple as in the single agent setting. Because, what's a natural kind of algorithm, right? I could just have each player do gradient descent, right? So I could just say, now update, right, my x according to some gradient, right? And similarly, y also updates. So it means here, sorry. So it turns out that if you're doing gradient descent, or we call it simultaneous gradient ascent, right? Because one is ascent, one is descent. It seems natural, right? Seems like a natural extension because, I was doing this with one player. I can do the same with two players. And I can simultaneously update both of them. So it turns out...
This means that you don't wait for the other one to
Yeah.
play and then
Yeah.
you do the same.
Yes. It's called simultaneous. And in machine learning, we kind of want more of these simultaneous updates, right? So whereas in game theory, there are kind of very different notions, right, of like how you want to optimize. and get to Nash equilibrium. And the reason is also maybe it's motivated by realistic scenarios, like one player really plays and completes some moves and then the other player takes over. But if I'm training a GAN, I just want to get to the answer as quickly as possible, right? So, and it turns out actually it's quite bad to not do it simultaneously. So this is a paper that'll be released soon, but I know. But the main idea is it's not really getting at Nash equilibrium, but I won't talk about it until the paper is out. That's an aside, right? But there's quite a bit of difference in thinking about, right, trying to get to Nash equilibrium from a game theoretic viewpoint and trying to train a GAN or any machine learning model, right? Because, these are not, right, agents with selfish objectives, right? We are assigning those objectives with a view to get robustness or properties like that. And so that's why in that case, it's desirable to do simultaneous updates. And in fact, good properties emerge from simultaneous updates. So this is the standard algorithm people do, or they do ADAM and do it simultaneously, right? So some form of first order optimizer, but done simultaneously. So it turns out, because we're almost ending the lecture, it turns out that even if I just took a very simple bilinear game, so bilinear is where it's linear in each variable, right? If you recall, when we are doing matrices and tensors, we talked about multilinearity, right? So this is a very special case. And it turns out even this very simple scenario, this diverges, it oscillates. So in the sense, each player just keeps moving, right? Even at infinite time, there's never any convergence. And kind of the intuition is because there's no curvature, right? So here, if it's a strict saddle point, like you're kind of having this curvature, you will get to that point. On the other hand, if it's bilinear, you're not getting that, right? So you're constantly kind of just going back and forth and you never converge. And so that's why, this kind of has issues, right? Whereas we know gradient descent and stochastic gradient descent converges when it comes to single agent optimization. And I posed this problem in the previous iteration of this class, and and that's when Florian came up with competitive gradient descent as a way to overcome these oscillations and to be able to kind of extend optimization to these min-max games.
Question. When we have, for example, bilinear form, isn't it because it's linear in each of them, you can change the whole problem to a linear program, right?
No, but it's linear in each, right? But it's
right,
still bilinear.
You can change it, just define that thing as value. What I mean is you can put whatever for the second agent to the constraint. What I mean, you can change a problem to be a linear programming.
It's bilinear, so how does it become?
I can show you.
I mean, you can always lift and do that, right? But then, that increases the dimensionality of your problem. Are you talking about lifting?
I'm not talking about lifting. I'm saying that for any function U that is linear in each of the parameters, this is a standard technique in game theory. You can change the whole problem to a one max. You can change it to a linear program. Yeah,
but on the higher order variables, right? That's called lifting.
I'm not changing. I'm not adding variable. I'm adding some constraint.
Or you add constraints. So you still have to do. I mean, ultimately, if you have to solve that constraint optimization, you need another minimax. So it's still not linear.
I can linearize it.
No, but when you linearize it, I mean, so there are other approaches, right? But the idea is in machine learning, I just want to use like simultaneous updates. So I'm saying this oscillates.
That's right. That's accurate.
And the whole idea is these simultaneous updates can be actually really powerful as a regularization for training GANs and other machine learning models. So that's why many of the other approaches coming from game theory don't seem to work very well here. So the CGD, again, I won't go into the details, but the main intuition is, right, you're looking at like kind of a local Taylor series expansion of your function that not only uses the gradient, but also uses the next derivative, right, which is the Hessian. But instead of like the complete Hessian, you only want the mixed Hessian that looks at interaction between the two players. So the main idea is here there is no interaction, right, because each player just updates only based on its gradient, and there's no information of what the other player is going to do. But if you had some idea of what the other player would going to change their move, right, then you can do it. And it turns out if you add like a Hessian information, right, you can do it better. And the question of how to add it in a principled way is what CGD does. So think of it as like you have a Taylor series expansion of what should be the, right, so at any point, right, so if I'm like looking at Taylor series, I can write it in terms of the gradient and then the Hessian. Right, and I can add like a quadratic penalty to account for the higher order terms. And so if I do this for both the players and then optimize that, right, like together, right, you ask what is the Nash equilibrium of this local approximation, it turns out to be the CGD algorithm. So again, I don't have the time to write it down, but the main principle is think of like local Taylor series expansion as a way to approximate what is the update of each player going to do, right? But include this mixed Hessian to account for what would be the interaction term. And you can solve this efficiently, even though it's a Nash equilibrium of this local game, but you can compute this in closed form. And so that's the takeaway behind CGD. Great, thank you.
Hi, I'm a science